Welcome to this explainer, where we're going to dive into a mind-bending paradigm shift that is completely changing the way we look at the universe. For decades, we've relied on these massive, billion-dollar telescopes to hunt for the secrets of gravity and quantum mechanics way out in deep space. But what if the answers to those giant cosmic mysteries aren't actually millions of light years away? What if they're sitting right on a laboratory desk? Today, we're taking a wild journey from colossal cosmic theories straight down to tabletop physics.
Take a close look at this quote. It's known as the lighthouse statement from the Bilingual Conformal Mapping Quantum Energy Integral, or CMQEI, Extension 3 white paper. I want you to really let this sink in because it completely flips our traditional understanding of physics on its head. Instead of thinking of the speed of light as some arbitrary cosmic speed limit, something you'd get pulled over for exceeding, it frames light speed as the fundamental architectural blueprint of space itself.
So here is our roadmap for today's explainer. We'll be looking at nature's first design condition, tabletop analog black holes, Theory 3.3 on space condensation, the AMPS entanglement triangle, and finally, the desktop cosmology era. Let's get right into it.
Section 1. Nature's first design condition.
To truly grasp this shift, we have to rethink how we view the speed of light, which we usually just call c. In the old view, c is just a constraint, right? It's something external imposed on the universe. But in the CMQEI Extension 3 framework, the speed of light is the absolute internal design rule that nature uses to build self-consistent structures. Under this new view, things like gravity, quantum mechanics, and electromagnetism aren't separate, disconnected forces fighting each other. They actually emerge as allowed configurations that are strictly dictated by this one primary boundary condition.
The CMQEI white paper beautifully maps out these 5 fundamental expressions of nature derived straight from this single light speed rule. Look at the very first one there. Gravity is reinterpreted as space condensation. I want you to keep that specific phrase in mind because we're going to see exactly how that works, both in theory and practically, in just a minute.
Section 2. Tabletop analog black holes.
Okay, to ground all this massive philosophical theory into something we can actually touch, let's talk about a groundbreaking 2026 experiment from the journal Nature Communications. This was done by Felipe Elizarraras and their incredible team. The setup looks a bit complex here, but the premise is just staggering. Using a 90-centimeter optical fiber, an ultra-short laser pulse, and a single photon, the team successfully created an event horizon right on a desk. Through a process called spontaneous four-wave mixing, they actually stimulated analog Hawking radiation. They literally built a tiny optical black hole to see how a single quantum particle behaves when it hits an absolute boundary. In this tabletop universe, our single photon has a very specific job. Well, actually, it has 2 jobs. First off, because a photon travels at the speed of light, it doesn't experience any internal time. This makes it the ultimate, perfectly objective ruler to test if light speed truly acts as a structural boundary when it hits an event horizon. And second, it acts as a door, crossing that intense boundary, which allows us to see exactly what happens to quantum information under extreme stress. This is exactly what connects the lab straight back to the CMQEI theory we just talked about.
So how does a tabletop setup compare to the real deal in deep space? Well, with astrophysical Hawking radiation, the process is entirely spontaneous. It's seeded by the highly unpredictable quantum vacuum. It's incredibly weak and essentially impossible to measure with our current tech. But the tabletop version is totally different. It's stimulated by a known, controlled single-photon seed. This means we can actively trigger the Hawking effect on demand and measure the output with high-precision single-photon detectors.
And the precision of those detectors gave us this mind-blowing number, 0.106. This is the heralded second-order correlation of the emitted analog Hawking radiation. Now, if you're into quantum optics, you know that a number significantly less than 1 proves you are looking at a single, indivisible quantum particle. This measurement is an absolute mic drop. It proves that passing through the analog horizon did not destroy the quantum nature of the particle. The statistical leakage was literally less than 0.04. The horizon acted exactly as CMQEI predicted, as a clean, self-consistent boundary governed by the speed of light.
Section 3. Theory 3-3, Space Condensation.
Now that we have definitive lab proof that quantum properties survive a horizon boundary, let's connect this back to how gravity actually functions under this new paradigm. If we look at the visual progression here, specifically Theory 3.3 on the far right, we can see space condensation in action. Because light speed is the ultimate boundary, energy starts to accumulate intensely at the horizon where the rule is strictly enforced. This accumulation physically condenses or pushes the spatial grid itself outward. Gravity isn't just some invisible pull, it's the physical gradient of this condensed space relaxing as you move further away from the horizon.
Out of the 3 models tested in the white paper, it is fascinating to see that Theory 3.3 just crushes it across the board, scoring a 44 out of 50. Why? Because starting from minimal boundary conditions, it mathematically recovers both the exact Schwarzschild geometry of a black hole and the Newtonian inverse square law of gravity that we feel every day on Earth. It's simply the most mathematically clear and unified expression of the lighthouse statement we started with.
But there's a catch here. Space condensation alone actually isn't enough to make the math work perfectly. To truly preserve that strict light speed boundary condition, time and quantum phase must condense simultaneously alongside space. This requirement ensures that the whole framework isn't just some neat geometric trick, but that it perfectly extends to the actual behavior of light and quantum information.
Section 4. The Amps entanglement triangle.
So, what happens to the information swallowed by these condensed horizons? At the heart of this paradox is the Amps triangle. It's a tripartite or 3-way quantum entanglement puzzle. It basically asks, is a particle falling into a black hole entangled with its infalling partner, or is it entangled with the Hawking radiation escaping to the outside? Quantum mechanics dictates it can't be fully entangled with both. That's a core rule called the monogamy of entanglement. To solve this paradox, we have to track all 3 sides of the triangle, which, as you might guess, is notoriously impossible to do in deep space.
And this is exactly where the tabletop setup has a massive, undeniable advantage over the cosmos. In an astrophysical black hole, the partner particle is trapped behind the event horizon. It's permanently hidden from us. But in our optical fiber analog black hole, that negative frequency partner is simply a different mode of light. It isn't lost to the void, it is right there in the lab. We can actually detect it and measure all 3 sides of the AMPS triangle at the same time.
To take this even further, the white paper proposes an upgrade known as the U3+ test. By using a Franzen-type Bell test, researchers can measure the exact decay of the CHSH parameter as pump power increases. By mapping this entanglement monogamy curve right there on a desk, we can definitively prove whether a horizon acts as a perfect unitary quantum interface. We are literally solving a cosmic paradox with laboratory lasers.
Section 5. The Desktop Cosmology Era. By merging optical fiber quantum optics with the CMQD light speed boundary condition, we aren't just doing neat parlor tricks with light here. We are genuinely entering a totally new era of physics. Just look at the spectral data from the Nature Communications paper. It proves that we can consistently spawn these bounded universes at will. The top graphs show the generation of a black hole horizon, which we identify by red-shifted light. The bottom graphs show a white hole horizon, identified by blue-shifted light. The researchers can tune their lasers to flip between the two, literally turning their optical fiber into a programmable playground for extreme astrophysics.
But to make sure this remains rigorous science, and not just a clever analogy, the framework establishes what they call kill conditions and cross-platform tests. These 5 parameters are the ultimate proving grounds. From checking if analog thermality perfectly matches Boltzmann limits to observing the linear Bright-Wheeler process, where colliding light literally condenses into matter. If the tabletop models fail these strict mathematical tests, the framework is disproven. This is what keeps the science honest and falsifiable.
Which leaves us with this final thought. We've seen how a 90-centimeter piece of optical fiber and a single photon can not only replicate the event horizon of a black hole, but fundamentally validate the CMQEI extension 3 theory that light speed is the structural blueprint of the universe. It really makes you wonder. If we can unravel the black hole information paradox and map space condensation without ever leaving the lab, what other profound, universe-altering cosmic secrets are hiding right now on our desks, just waiting for the right laser pulse to reveal them? Thanks for joining me on this explainer. I really hope it changed the way you view our universe.